Hello everyone. Last session we talked about virtualization as one of the main enablers of cloud technology. Today we continue the discussion on other enablers of cloud computing technology. So these factors or these enablers are definitely less important than virtualization. However, they have played their own role on the current status of cloud computing. One of the important factors in cloud computing, or better to say, that enabled cloud computing, is service-oriented architecture. Service-oriented architecture is a software methodology topic, so it is not directly related to this course. However, we use cloud computing, SOA or service-oriented architecture in cloud computing. So we discussed the SOA or service-oriented architecture in the previous chapter when we were talking about web services. So basically, web services or even RPC is the idea is to make one application loosely coupled and enable different parts of it talk to each other. Basically, each part of the program, specifically in web services, is to be disjoint from another part and be hosted on potentially a different server owned by a different organization. So SOA is, to the extent that is related to this course, is the same idea. Basically, how to break one application or pieces of one application be hosted on different computers, whether or not they owned by one or multiple organizations. So basically what SOA does is making the application loosely coupled, different pieces of an application loosely coupled. Again, the example would be, let's say, purchasing online stuff using Amazon and then do the purchase option or the payment part via another service provided by Visa or Masters or different credit card companies. So this is one very obvious example of services. However, going beyond that, even pieces of Amazon can be done using SOA. For example, when you purchase an item, or when you search an item, it suggests you some other similar products. So that is done via a service. That's a microservice. A microservice, because I use the term, I want to explain it, is basically same idea of a service, is making the application from independent parts, reusable parts. Each service / microservice is independently usable, and it makes the application loosely coupled. Generally, we call it microservice because the idea is that to break each function and make it as a service, and that's why it's called a microservice. So let's say in the case of Amazon, the part that shows us different similar products can be done using a microservice. There are numerous examples like this. For example, if you write an application and does the storage on Google Drive, you may use Google Drive web services to incorporate that within your application. All right. So basically, as a developer, you can build application by composing one or more of these microservices without knowing their underlying architecture. Suppose that if you are the programmer of the Amazon purchasing system, online purchasing system, you don't need to know the details of implementation of other similar products. You just call a function and that is provided to you. Similarly, you don't need to know about the details of the payment. You just call the web service and that is done for you. All right. Another advantage of advantage of SOA is the ability to call it via different programming languages. For example, a microservice might be implemented in Java, but you can call it using Python. Specifically, this is possible when you use technologies like web services or gRPC that we discussed in the previous chapter. All right. Another enabler of cloud technology, what basically transitioned um, uh, from grid computing to cloud computing, is called economy of scale, or I would call it the commercialization of computing. So that happened because of what is known as economy of scale, in which a product is becoming beneficial for the provider of it when it is produced in large scale. So basically, you may have experienced that when you buy an item individually, it is much more expensive than when you buy it in bulk. So similar idea happens in computing domain. So what happened was that in around 2006, 2007, and since that time, basically, many strong companies came to this market and built very large scale data centers that could offer computing and services to people with a low cost because they provision that and they own that in large scale. Therefore, the amortized cost for things like um, cooling and electricity and staff is amortized. Therefore, they pay a lower cost. All right. So a data center is generally has numerous servers. Something from 400,000 to 1 million server is not a surprising scale of a data center nowadays. So this is an example of a Microsoft data center. The location of these servers are generally not known, but they are scattered all over the place, worldwide or countrywide. And you can see that they generally have their own electricity sources, they generally have their own cooling facilities, and they are built in a modular manner, as I will explain later. So let's look at the internal architecture of these data centers. So, and by the way, I want to uh, remind you that data centers are a little bit different than supercomputers. So data centers are more known in cloud computing terminology, where we have numerous resources, but each one is a normal computer. However, in HPC systems, in supercomputers, the whole system is forming a big computer. So that's a big difference between them. Here, we have a big cluster. Each node individually is a normal one, but we have it in large scale. All right. So within data centers, what is going on within data centers? So not much from what we have discussed in the previous chapters. It is composed of racks. Within each rack, there are numerous servers. It really depends. There are sold in different sizes and with different capacities. So each node has a multi-core CPU and cache and RAM like an individual computer. I would like to tell you that there are other emerging architectures for data centers where they are called disintegrated data centers, in which or disaggregated data centers in which each component is managed separately. Let's say we have only RAM servers, we have only compute servers, we have only storage servers. But this is, I would say, is more on the research domain. What we have in practice is more like conventional data centers, which is in which each node within a rack is an independent computer with its own memory and processing and cache. All right. So the nodes are located within racks, and the racks are connected via a network through the data center. So within each rack, we have a switch, a network switch that enables communication within that switch, and then of course the communication with what is so-called the core switch. We can imagine or we can visualize the network architecture of a data center as we can see in this figure. As we can see, within each rack, we have a rack switch that enables the communication within that rack, and then we have a core switch that enables the communication with the external world, with the rest of the internet, and enables the communication across data center. You can imagine that the bandwidth and the communication delay within a rack is much shorter than the communication delay across racks. So the ratio is sometimes 10 times faster to communicate locally as opposed to communicate across racks in a data center. So for example, in intra-rack, we can have something like 1 gigabit per second bandwidth, whereas across racks, we can have 200 megabit per second. But these are just examples. The current technology probably is going beyond these numbers. So in data centers, as we discussed in the past, we have around 1% failure rate. However, because we have numerous computers, even that 1% causes a lot of failures within a data center and at any single moment. So you may ask how these data centers are built. So they are generally built in a modular way using ready-made containers. So there are companies whose job is to build data centers. These companies generally produce produce racks and computers within them and configure them all together, and they ship them using trucks, and then they just aggregate them in the destination location. So you can imagine something like that, and then they just aggregate all these modules together in the destination place. So another feature or another aspect of data centers is the cooling aspect. So data centers generate a lot of heat, and heat and cooling actually is one of the main sources of expenditure in cloud data centers. So nowadays there is a huge research going on in cloud data centers to cool them down with a minimum cost, because that's a recurrent cost. Saving on it would benefit data center owners a lot, and also makes data center and computing industry greener. So the data centers have their own specific cooling systems. Generally, we have systems called CRAC, computing room AC systems, or CRAC units, where they push cold weather to the data center, and they observe the hot weather from the data center rooms. The efficiency and the power efficiency of data centers are measured based on a factor called PUE, power utilization effectiveness. Intuitively, PUE is calculated as the total power consumption of the data center divided by the um, the power required by the IT equipments, basically by computers. So basically, the ideal value for PUE is 1. However, in practice, we do not have PUE equal to 1 because there is a lot of overhead costs, overhead energy consumption. In practice, the normal PUE is something like 1.69. We can say something around 1.7, which shows that almost around 70% of the power consumption is used for cooling. All right, so now we talked about the enablers of cloud computing. We discussed main technologies that enabled current cloud system that transitioned us from grid computing platforms in 2000 to cloud computing platforms in 2010 or around that time. So, but what emerged as cloud computing had different forms. They were not all having the same form. They were offering different services. So we can categorize the services offered by cloud providers as follows. One of the popular types of cloud systems are known as infrastructure as a service. Another one is known as platform as a service and software as a service and eventually function as a service. I would say that as we go from number 1 to number 4 or even beyond that, we get a higher access to the cloud systems. In fact, when we go from infrastructure as a service to function as a service and software as a service, we get less access to core resources, but it is easier to work with. So basically, in software as a service and function as a service, you do not feel that you are using a cloud system. I'm telling that to tell you that it is so high level access to cloud resources in SaaS or software as a service or function as a service. So you are not engaged with the low level and details of the services offered by clouds. However, in infrastructure as a service specifically, you are more engaged with all the details of the system. So you have more flexibility in infrastructure as a service to configure your system, but it is a little bit more difficult to work with. So we can see that cloud computing, in a general way, they provide what is known as X as a service. So basically, they make anything as a service. So many companies nowadays are built based on this idea. And what they do is just get different services from different companies and they mash them up together and generate a new service. Let's say if you want to have a new video streaming company, so you get storage from one company, you make computing from the same or another company, you get CDN from another company, and you get the services from them, and you just mash them up together and create a new service for your users. All right. So let me discuss each one of these service models. Infrastructure as a service is the most popular type of cloud that professionals are dealing with. So in infrastructure as a service, users receive a virtual machine, generally a virtual machine, and they have to configure that virtual machine for their needs. So for example, if you want to configure a web hosting server, basically providing an HTML content to your users, you use infrastructure as you can use infrastructure as a service type of cloud. So you are given a virtual machine, as we discussed in the past, and then within that virtual machine you have root access, so you can install and configure whatever service you want, and then that virtual machine has public URL and IP address, and anyone around the world can connect to that virtual machine and work with it. So we talked earlier on how virtual machines work. They use hypervisors such as Xen or KVM generally, or VMware also is used very much. So in this case, users of the VMs or users of the cloud have root access to the machines that they create, to their virtual machines. So they have a lot of flexibility on the application stack they want to install on their machines. So cloud users are generally charged in an hourly basis on a pay-as-you-go manner. So basically, for the amount of time you are using cloud resources or virtual machines, you are billed. Let's say it depends how powerful is the VM you are using. So basically, if you use a virtual machine with 4 cores and let's say 16 gigabytes of memory, and 256 megabyte of cache, then this may cost you a couple of dollars per hour. If you reduce some of these features, you may pay a little bit less per hour. So many cloud providers offer infrastructure as a service services, and the most popular one is Amazon, that offers infrastructure as a service known as EC2, Elastic Compute Cloud. Google Compute Engine is another example of popular companies offering infrastructure as a service model. So platform as a service is one level higher. It doesn't give you root access to install things and have SSH to destination virtual machines and things like that. They generally offer you a platform. That platform can be something like a programming language. If you use a PaaS service, you do not need to install any programming language. Let's say if you want to program Python, you just use that online service, and then you write your code. You do not care about the underlying hardware, the amount of memory, the number of cores. They are all provisioned, and you just run your code. Or it can be, let's say, in form of a database server, or it can be in form of a web server. So you get a platform, or even an operating system. So but the operating system in this case, you just have access to it. You cannot manipulate that. So, and then developers run their softwares on this platform as a service models. So the good thing is that you don't have to deal with the complexity of purchasing and maintaining those resources, and it is easier to work with. So Amazon Cloud also offers PaaS services. For example, it has a service known as Amazon Beanstalk that is enabling you to configure a web server, or Amazon DynamoDB, which is a database systems. Also, Google App Engine and Microsoft Azure are considered as platform as a service. Other examples are Heroku and Jelastic. Software as a service is even one level higher, and it gives you access to a certain software. For example, your university may use Microsoft email system just to offer emails to its students and staff. Like that, you log into Microsoft services, Microsoft, let's say, email services via your credentials, via your institution credentials, but in fact you are using behind the scene, you are using the services offered by that company. SaaS is the most popular type of service that normal users are using. So many of us, many of people in the society nowadays do use cloud services in SaaS model without knowing that they are using clouds. So as I said, in this SaaS model, you just use a software. That software can be a accounting software that you use in your company. It can be your email service. It can be your the portal for your company that offers different services. These are all can be done using software as a service. So the pricing model for SaaS servers is typically in a monthly or a yearly flat fee. So for example, your university may pay some known amount to, let's say, Microsoft to support us for an academic year. So this is their business model. So they offer you the look and feel of ownership. So for example, if you want to log in, you don't need to use Microsoft credentials. You use your own university credentials. And then maybe even if when you log in, they may show you the logo of your own institution, so you feel it is yours. But behind the scene, in fact, your institution does not own any of those services. It's just rented to be used for your company. So Google Docs is an example, another popular example of software as a service that many of us have used. So let's say in Google Docs, we get an editor as a service, or Google Spreadsheets, or Google Presentations. These are all examples of SaaS, or software as a service clouds. All right, a more recent cloud technology or service model in clouds is known as function as a service, or FaaS. So in this model, I would say from some aspects this is similar to infrastructure as a service, but not entirely. So the problem with infrastructure as a service is that it is a little bit difficult or it needs some expertise to configure that. Another problem is that once you create a virtual machine, you have to pay for it even if you don't use it. So for example, if you create a virtual machine and for whatever reason you do not utilize that, but you are still charged because your virtual machine is being available for your users, although they are not using it. So function as a service is built based on this idea. In function as a service, instead of having a virtual machine, you just have a function, a part of your program that is executed by cloud. So it also is similar to platform as a service, because in FaaS, or function as a service, you have to develop your function, and then that function will be hosted by clouds. So because it is more about development, we can say that it shares some similarities with platform as a service. So the good thing with function as a service is that there is no fees for hosting that. However, you will be charged only if the function is called and is used. So otherwise, there's no fees in using function as a service. Therefore, the way function as a service is used is in a passive manner. So basically, you write your code for that specific function and you handle it to cloud. You hand it over to cloud, and then that will stay there until a request comes in. So once the request comes in, that function is triggered. We can say that service is triggered, and then it performs the function that it should, and then sleeps again, waiting for the next request to come in. So it has some passive nature. You are charged only for the time that your function is executed, and for the other parts of the time, you are not charged. This service model, over the past few years, past couple of years, has become very popular and has formed a new concept in computing known as serverless computing. So in serverless computing, this is more in compared to what is known as infrastructure as a service. In infrastructure as a service, although you use cloud services, but you have to configure your virtual machines, configure the access to it, configure load balancing for it, configure latency for it. So it has still a lot of implications to handle. However, in function as a service, you first pay less, and second, you do not need to deal with the details of scaling and elasticity and latency and all these things. So basically, you just hand over the function to cloud, and then cloud will handle it for you in terms of how many whatever number of users you have, it will be scaled, and it provides a predictable response time to the users. So you, as the user of cloud, you do not have to be worry about the load balancing, the scale up and scale down of your resources. In Amazon AWS is the cloud version or the cloud part of the Amazon company. It's known as AWS. They have a service called Amazon Lambda. So this Lambda is in fact an example of function as a service service model. So generally, function as a service are provisioned using containers. So companies do not use virtual machines to handle functions as a function as a service. Each function is allocated to a container and is run within that container. So an example of a function as a service can be a video transcoding. Assume that YouTube, for example, uses, or something like a YouTube service, uses function as a service for transcoding. So whenever a new video is uploaded to their server, the transcoding function is invoked to process that video and convert it to the format, to the standard format of that provider, and store it in their cloud storage. And after that, it sleeps again until the next request comes in. So this is a perfect example of how function as a service can be useful. So in this case, you don't need to be worried about the number of users, if the number of users go up or down, how to scale, how to make sure that the latency is within a certain amount, and things like that. For this reason, it is called serverless computing. So when we say serverless, it does not mean that you don't have a server. It means that you, as the user of this system, do not see the server. So the server, as if there is no server, but the server is there. It is a little bit of a misleading term. The service is still there, but you just do not see that. All right. So cloud systems can be categorized based on their deployment model, how they are deployed. In particular, cloud systems can be private, public, hybrid, or other forms of deployment, which is like federation based. Basically, multiple clouds get together and form a bigger cloud. So I will pass these parts faster because we have discussed them in the earlier parts of the course. In a private cloud, of course, it has more security and it is limited to an organization. So the users of it or the owners of it have total control on it, and it is configured based on the regulation and policies of one organization. Public clouds, on the other hand, uh, is things like Amazon EC2 or Google Cloud that is accessible to everyone. Obviously, it has some security concerns. That's one of the problems. And but it has numerous resources, and they are very strong on elasticity. On private clouds, we do not have so much of elasticity, meaning that the resources can be stretched or squeezed when you do not need them. So, but the public clouds generally are paid. You have to pay to use them. And they are very large scale, of course. So we have what is so-called the community cloud. A community cloud is a federation of clouds that I will explain it in a few slides later. This is a table comparing public clouds and private clouds from different aspects. I already explained some of those aspects, but here we provide a more comprehensive comparison between them. So in terms of ownership, public clouds, of course, are owned by some companies, some generally big companies, small, medium level companies cannot afford such services. So this is mainly limited to big players such as Amazon, Google, Microsoft, and IBM and things in that level. However, private clouds are generally owned by an organization, and they generally leverage their existing resources. Let's say they have had their own cluster, Slurm cluster or whatever form of cluster, and then they kind of promote it to be a private cloud. So when we promote it to private cloud, it is just it depends to the user, it depends to the use case, but sometimes it makes it easier to work with and easier to maintain. So in terms of management, so these are managed, of course, by remote companies, by public companies, and they generally use VMs nowadays, a little bit of containers. They have some proprietary infrastructure. For example, we really do not know the type and the platforms that, let's say, Amazon and others use. They customize it for that. Whereas in private domains, in private clouds, of course, they are managed locally by their staff, and they use standard tools to configure that. And they may have some lower latency because of being close to the users. So having lower latency and higher security is the advantage of private clouds. So in terms of workload distribution and loading policies, again, public clouds use virtual machines and use load balancing techniques to distribute data or the workload to the VMs, and they have the elasticity feature. On the other hand, private clouds do not have elasticity, and they may use containers instead of virtual machines, but also virtual machines is very popular in the private domain. So in terms of offloading, although public clouds rely on elasticity, so have the elasticity feature, I can write it here, elasticity. But private clouds do not have that elasticity. They gain that elasticity by connecting to the public clouds. So a private cloud can use a public cloud as another source of, as a backup source. When there is a peak demand in the private cloud, then the public cloud is come to play for offloading purposes. In terms of security, I mentioned that public clouds are, one of their problems is the security concerns, and this is very important for some, let's say, financial or healthcare companies. But private clouds, of course, do not have that problems, so they are more limited, and they can enforce organizational policies. And there are numerous examples of each type of cloud. I would say on the private cloud side, nowadays the popular platform is OpenStack. So if you want to build your own cloud, you just need to install OpenStack on your cluster and you have a private cloud. All right, so I mentioned that when there is, in a private cloud context, let's say this is a private cloud, when there is high demand, the request can be redirected to a public cloud. Let's assume this is a public cloud. In this case, the request can be redirected to public clouds. So this forms a hybrid cloud together. This is known as a hybrid cloud. So we have a scheduler, or sometimes called load balancer, that basically determines based on the load situation on each machine or on each cluster whether or not to redirect the workload to cloud or not, or which part of the workload. Probably if you have security concerns, the parts with lower security risks can be better candidates to be redirected to public clouds. Another way of enabling elasticity, is basically connecting multiple clouds together. There are some ideas known as intercloud to connect multiple clouds together. So basically, for each cloud, we can apply what is so-called the gateway. These are gateways, and these gateways they have a prearranged connection with other clouds, and then at the time of a peak demand, they can redirect requests to other clouds. So this is known as intercloud. However, there are concerns about interclouds because it is rare that we can convince several companies to trust each other and basically balance their workload between each other. Second of all, this manner of working across should happen through internet. So it needs a huge bandwidth, which is not accessible in the public internet. So, and as I said, because the companies are generally competitors, it is not very conceivable to, let's say, Amazon and Google form a federated cloud. This is not conceivable at this time, at least. However, some alternatives of these scenarios are conceivable. For example, within a town, we may have multiple clouds, and those or multiple organizational clouds, better to say, and then they can work together. Let's say at a disaster time. Let's say when there's a flood in an area, the clouds of hospitals and the military systems and schools can get together and form a bigger cloud that can satisfy the local requirements with low latency in a specific region. This is known as community cloud. Another fashion of working between clouds is called multi-cloud. Although intercloud, there are major concerns about their feasibility. Sorry, multi-cloud, which is built on the idea of brokering, is a more viable solution. So in this manner, there are companies that basically they do not own the infrastructure, but they buy infrastructure from different cloud providers, and then they sell it to the users. So the user deals with this broker and does not see behind that. And then this broker buys resources in bulk and then sells it with a higher price to the users. In this scenario, this is also can be considered as a type of intercloud. However, in this manner, the clouds do not directly cooperate with each other. Instead, they cooperate via this broker. Alright, here we conclude this chapter. In this chapter, we mainly talked about enablers of cloud computing. We talked about virtualization, VMs, and containers as the most popular virtualization techniques in cloud computing. We also discussed virtualization as one of the main or the main enabler of cloud systems. We also talked about other enablers of clouds in terms of service-oriented architecture and economy of scale and other facilities that basically transition grid computing to what is known as cloud computing. So we also talked about different service models of cloud systems and different ways that clouds can work together. Thank you and have a good day.